All right, folks. So this is a short session. It's only got two talks, but they're very interesting because they're both talking about this design abstraction or like language abstraction that shows up often with concurrent software programming languages. And I'm really excited to hear how our speakers are trying to take that abstraction and build sort of support for it in HDLs. So I think we'll start off with Andrew first. Andrew, do you want to share your screen,
Sure thing. Yep.
please? Great. So Andrew from UW is going to tell us about how to build cache coherence using coroutines. Andrew, take it away.
Great. Thank you, Rich, for the introduction. So, hey, everyone, I'm Andrew, and I'm going to be talking about modeling the MSI cache coherence protocol in an HDL with coroutines that I'm developing with my collaborators that are all listed here. So, as many of you know, a lot of hardware consists of interacting FSMs. And so, in our model of the MSI protocol, we're modeling two FSMs, which both communicate with each other and share access to the L1 cache, which the coherence is being maintained over. The processor request FSM on the left deals with incoming read and write requests from the processor, returning results from the cache when the data is available and in the correct state, and otherwise dispatches requests to the bus FSM on the right to pass along to other processors or the rest of the memory system. So to illustrate how this model works, we can step through an example read request, which first looks up the result in the cache, and then goes to its counterpart module, FSM, which forwards the request along before returning the data to the processor. The bus interface FSM also has to handle requests from other processors while simultaneously serving its processor. So in this example, suppose another processor wants to upgrade its permission for a cache line at address 0xc, while the bus FSM is processing the request and interacting with the cache. It must temporarily stall requests from the processor FSM, which is a typical interaction pattern in managing shared resources in hardware. Now, this example has some fiddly details with all the interaction, but we can simplify this and just zoom in on one part of the left FSM and observe how it just handles read requests and see the complexity there. So it starts in this wait for request state, spinning until it gets a request where it looks at the data and proceeds in the hit or miss direction. Now, while the specifics aren't super important here, the key idea is that there's actually only two paths that processing this request takes. It's either branching on the hit or the miss. But if you look at sort of a standard Verilog implementation of this sort of protocol, the structure is completely flattened, and your brain is in charge of sort of reconstructing the FSM diagram on the right. The situation is made even more difficult when the designer has to both reconstruct the structure of the FSM and consider incoming requests that we simplified away earlier, or like hand-waved away earlier, from other FSMs expressed in this flattened style. So I guess the question is, how do sort of coroutines how would an HDL with coroutines for writing FSMs improve this situation? So we'll start by looking at the beginning of a coroutine hardware module written sort of like a Python-like syntax for handling the read requests, sort of like we were looking at before. The timing model of our HDL is such that the coroutine is invoked once every clock cycle and runs until the yield statement. So inputs to the coroutine correspond to inputs to the module. The body of the coroutine contains a while true loop to correspond with the sort of non-terminating nature of hardware, as it should also be sort of a behavioral simulation of the eventually synthesized circuit. The first block of statements in the while true loop is the code that corresponds to waiting for a request state, and yields empty, invalid inputs every cycle that it is not getting a request. And note that the yield returns the inputs for the module in the next cycle, which is where execution resumes. So if we add the code in for the next two states following the sort of the cache hit path, you should note that the data variable defined by the cache lookup and then later returned in the yielded valid out object needs to correspond to a state element because it persists over the yield boundary. So in other words, because its value is needed in multiple cycles, it must be stored in a register. And so the synthesized circuit must infer a state element there. You'll see that the yield after the cache lookup ignores the value it returns because the module is in the middle of processing a request, which is an important signal to help the developer reason about how to compose this FSM with its counterpart FSM. This explicitly says you do not have to worry about what happens if you receive inputs here. It additionally creates a contract for modules providing input that anything that they send to this FSM at this moment will be ignored. If I add in the logic for the mishandling, and don't worry, you don't actually have to read through any of this, you'll notice that it's actually structured in the way you'd expect the protocol definition to be structured. The control flow paths are explicit, and there's context around each individual state transition, i.e. the code around the yield, and it's not just some sort of flattened mess jumping around from state to state. So just to recap the features of this language, we're working on, in this language, a top coroutine is invoked once per clock cycle, which then steps all of its child coroutines, and effectively every yield point is a time boundary. As such, a yield must exist on every control flow cycle, otherwise this is expressing a combinational loop, which violates the abstraction boundary we're intending this language to design at. But the main point I'd like to make is that coroutines nicely express control-heavy protocol implementations like this and are a promising abstraction for future HDL developments, which may also help lightweight forms of verification early in the design process since intent is more clearly expressed. I appreciate you all listening, and I look forward to your questions in our discussion later.
That was exactly 5 minutes. That's remarkable. Thank you, Andrew. Next up, I think we have Florian to talk about more coroutines. Perfect. Take it away.
Okay, hello everyone. I'm Florian. I'm from Graz University of Technology, from Institute of Technical Informatics, specifically the Embedded Architectures and Systems group. And I want to continue to talk about coroutines by talking about my hardware description language, which I call Prost. So as we heard in the last talk already, the basic idea here is that coroutines can be the fundamental abstraction of hardware description languages, and I think they should be. For some bullet points here, coroutines can express algorithms directly without having to convert them to finite state machines first. They can also express most combinational logic directly, which is very nice because we need those, of course, as well. For many people, I think it's also very nice that they read like functions. If you're a software developer, you can suddenly read hardware code without doing a few semesters of taking courses on it. And also very important, they compose like functions. I want to talk about this part a bit later as well. My hardware description language looks very rusty, but I want to give a very quick introduction into it. Here's a simple task written in my language. It's called Mac. It takes in two arguments. One of them is a single bit signal input, and the other one is an integer signal as an output. It's initialized to 0, the output, and then we have an endless loop that does the actual operations. Here you can see that it takes the current value of the accumulator, multiplies it by the return value of Rx byte. However, Rx byte itself is, when called, returns a task that has to be waited on. So this is actually a second task, which if we look at it, takes in a signal, so Rx before, and essentially has a loop inside that reads out 8 bits from a bit stream. Between each of the bit streams, it waits against 250 cycles through the single bit. And this again is just a task that has a loop that runs for 250 iterations. And in each iteration, it calls this wait statement, which is similar to the yield we saw in the last presentation. Now, what's interesting here is that this reads like software code, but it can be synthesized very straightforwardly. We first identify all states. We can simply go through the code and look for a single wait statement. So this is not the dot wait syntax, but the wait semicolon you see in the very end. And at this point, we can define the states as not just the statement, but also all the locals that are currently in scope, plus the entire stack. So every local that is in scope in any of the caller functions. We then look at the control flow between these states. So from this wait statement, where can we go? How do the values change during that transition? Essentially, what this ends up being is we convert all of these tasks, combine them in a single task, in which we unroll all the loops, or they become branches, and all task calls are inlined. This is kind of a problem that I want to talk about later a little bit as well. Then once we have states and we have control flow, we just on reset enter the initial state, and on clock advance to the next state, and we have functional circuit design. Now, there's a bit of a problem here. This is maybe a bit too good to be true. Coroutines are actually very powerful. They can express a lot of things, and some of the things they can express are not synthesizable for hardware. Mainly the one thing that concerns me is that if we want to have a compiler, it should only allow synthesizable code, or at least give warnings on code that's not synthesizable. We have a problem here that between two state transitions, there needs to be a bounded amount of time. but coroutines allow us to express things like infinite recursions and infinite loops that may not ever reach this wait statement. And statically checking for this is undecidable in computer programming. So we need to have some restrictions here on how we can restrict our code input, restrict coroutines so they're always synthesizable. For example, we can say every loop must contain at least one wait statement. That's a simple approach. Or maybe we can additionally say, or it needs to be unrollable in 10,000 iterations or something. But there are good semantics missing here that need to be researched further. Signal assignment is kind of difficult. In the last presentation, we saw how you can have yield statements. You basically return the current state with the yield statement, and then the next step you resume with the arguments. I've here opted for instead capturing all locals implicitly. I'm also capturing the signals. But now the question is, if I read the value of a signal after I just changed it in my code, has it already the new value, or is this value only changed at the next clock cycle as it would be for register? I think this is the more logical approach for synthesis, but it's also a little confusing for local reasoning. Finally, the last two problems here is how do we do multi-clock circuits? This is a little difficult with coroutines, other than just splitting the entire circuit into clock domains. And can we model intentional combinational cycles, such as latches as well here? Yeah, that's basically it. Thank you.
Thank you, Florian. All right, folks, we have 10 minutes for our group discussions, so we'll reconvene at 11:51. Great. So we're going through the questions. I think here's an interesting one, which is essentially there's a bunch of different kinds of abstractions people have proposed to manage communication. So coroutines is one, and there's also message passing abstractions like send and receive. I think the question is basically, what is the relationship between message passing based HDLs and coroutines based HDL? So would either or both of you like to take a crack at that?
I think I'm not too familiar with message-based coroutines, message passing-based coroutines, other than from the object-oriented abstraction of message passing, but I'm not sure if this is what this is talking about.
An example would be something like Google's XLS, which is this message passing high level for like DSL for designing hardware.
Yeah.
Okay. Yeah. If Aaron is more familiar, go ahead.
I wouldn't say I am more familiar, but I mean, I think in the coroutine model, there's more focus on sort of the timing abstraction rather than sort of like passing data. I don't know. I mean, I think that's just kind of an obvious answer, but I mean, the idea of a coroutine is you're expressing a sequence of states, and I'm not sure sort of message passing hardware description language has that sort of abstraction as well. Yeah, I'm not sure though.
Would it be correct, Cassandra, that message passing is maybe a thing you could implement with coroutines because it's sort of a higher level abstraction? Would that be a reasonable framing or something? I'd also be curious if there are any message passing experts in the audience who want to shout out something about this. It seems interesting.
Yeah, I mean, one thing you could do is your sort of send operation is just yielding some piece of data to your caller, and your receive is just spinning in a loop and waiting for that thing to come back. You're blocking receive rather. So I mean, that seems like a reasonable thing to do. Yeah.
Another question that came up was, how do you express other kind of microarchitectural features like pipelining in this model? Because coroutines give you this benefit of like expressing FSMs really cleanly. But like, for example, if you don't meet timing and you have to like break a combinational path, you're going to have to insert a yield point or like a wait point in Florian's language. Would that mess up things, or does it just like work out nicely in the abstraction?
I can say that at least in prose, the idea is that tasks are actually first-class objects. So when you can decide for yourself when you advance them or not. In principle, this means if you have implemented some coroutine that has 5 wait points, the caller could actually pipeline this in the sense that I instantiate it 5 times at different positions in the pipeline, and then keep those 5 running separately. Of course, here's the big question: if a synthesis tool or a compiler could implement this in such a way that it doesn't duplicate the resources used between, that it shares the used resources between the pipeline stages. There could also be language built-in variants for expressing pipelines the same way of coroutines. There are some languages that do that already. Silas, for example, does this. And the final option for me that I want to rely on, but I don't think I can right now, is ideally I would just want to add pipeline stages at the end and have the compiler figure out the retiming for me. But of course, this is probably not what most people are hoping for from low-level hardware description.
I guess maybe to refine my question a little bit, or this Victor's question a little bit, does pipelining change the interface to a coroutine? I.e., does the external world get to observe that you're internally pipelined? Because if they do, then they must perhaps adapt. If they don't, then that's really nice because you can sort of keep everything abstract to the outside world. And that seems powerful.
Yeah, I don't see why you couldn't pipeline something and hide it from the caller. That's not a problem. In the end, the answer is always here: you can do it as a state machine. If you can do it as a state machine, you can do it as a coroutine. So you can hide it for sure. I think it's also a possibility to maybe have some way to wrap a coroutine that's not pipelined and make it magically pipelined. But that's a bit more advanced.
Yeah, I mean, I think one thing that's difficult is that in hiding the pipeline stuff is that your latency interface sort of changes there, right? Like instead of calling something and immediately getting the answer back sort of in the next call to step, you have to call step a bunch of times for the coroutine. But I think like actually implementing the pipeline certainly feasible. But yeah, like Florian said, you can make a task for every pipeline stage and then sort of just wire up their dependencies between each other and pass around the hazards, and sort of like higher level coroutine that's doing the pipelining. So that probably made no sense hand waving around, but yeah, I think happy to talk to anyone about that.
I think perhaps the last question, just because we're going to go to lunch soon.
Sorry, I just have
Yes,
one.
please.
Like, I don't know, maybe what you want is to have the pipelines be totally external to the coroutine thing. Is like maybe what you want is if you have sort of like deeply pipelined logic that takes like 5 cycles or something, you want the abstraction to be that like you've got your FSM over here and it like sends some things into the pipeline written in a totally different style, not a coroutine style. It like feeds through the pipeline and then you pick up the results in some future cycle. Like maybe you just want to communicate externally with the pipeline. I don't know, just a random idea for you.
Yeah, I think that makes total sense. I think if you're tolerant to sort of variable latency of like this might come back in 1 cycle because it's not pipelined, or this might come back in 10 cycles because it is pipelined. Like as long as your coroutine is sensitive to that, which it should be, which if you write it like that, yeah, that makes sense.
Sweet. With that, I think we're on time for lunch. Let's give our speakers a round of applause.